This is video on kinematics of particles. This is the fourth video in which we are going to now talk about curvilinear motion, and this video is devoted to the derivation of the basic equations. Now, before we get into the equations or the derivation, we need to talk a little bit about unit vectors. Let's say particle is moving along this path. The path variable is s, meaning the distance along this path will be s. Now, all of us, I'm sure, are familiar with I, the unit vector along x-axis, the j, unit vector along y-axis. Normally, velocity and accelerations are expressed in terms of I and j. But here, for the purpose of study of curvilinear motion, it is found convenient to introduce two new unit vectors, and those are tangential unit vector Et and normal unit vector En. Let's say at a given instant the particle is here. Then along the tangent, if we defined unit vector, it will be called Et, and normal to the tangent we define a unit vector which is called En. Now you see, I, unit vector I is constant vector, meaning its magnitude is 1 and direction is always along x-axis, and so is the case with j, magnitude 1 and direction always along y-axis. But in case of Et and En, what happens is once particle moves from here to, let's say, here, the direction of tangent and normal at that point changes, and therefore if we define unit vector as unit vector along tangent and En as unit vector along normal, then these vectors are no more constants. Of course, the magnitudes are constant, but direction keep changing, and therefore these are not constant vectors at I and j. But in spite of this, we find that for many problems it is convenient to express velocity and acceleration in terms of Et and En rather than I and j. So what we are going to find after our derivation is velocity will be ds by dt into Et, and acceleration will be d square s by dt square into Et plus ds by dt whole square upon rho into En. Now we are going to look at the derivations of these equations. First, let's talk about v is equal to ds by dt Et. Let's try to derive it. For this purpose, we take this path of the curve and we say at any time t, let the particle be here, where position vector is position vector in terms of xy coordinates is defined as r bar. After time t plus delta t, let particle come here, where the new position vector is r plus delta r, and if you can complete this vector triangle, this vector going from its position at t to position at t plus delta t will be called delta r, and we will call distance along the curve between these 2 points as delta s. Now, by definition, velocity is dr by dt, which by definition of derivatives we can write as limit delta t tending to 0 delta r upon delta t. Now, delta r is a vector, so you can always write it at magnitude, its magnitude into and multiplied by direction, a unit vector along direction. So I write delta r upon delta t multiplied by unit vector along delta r. Now see carefully. What happens is, in the limit, when delta t tends to 0, this point starts coming very near to this, and in the limit we will agree, I think, that the magnitude of delta r approaches distance delta s along the curve, and unit vector along delta r, that is delta r's direction, in the limit becomes tangential to the curve at this point, and that is the direction of Et, and therefore we say unit vector along delta r coincides with Et. And if we And also one more thing, in the limit delta s by delta t, delta s by delta t, limit delta t tending to 0 become ds by dt. And therefore, putting all these things together out here, we can write v is equal to ds by dt into et. And that's our first expression. This t here actually should be delta t, delta t. There's a misprint here. Alright, but we have this expression v is equal to ds by dt into et. Alright. Now, let's go ahead and derive acceleration expression. So, let's do like this. Let's take again a point at time t and t plus delta t, and let the tangential unit vector at this point be et. And since we already said that it is not constant, let after t plus delta t, let this tangential vector become et plus delta et. Let this be center of curvature, let rho be the radius of curvature, and let distance along the curve be delta s, and let this small invalid angle be delta theta. Now, if we reproduce these vectors here, we draw parallel to et, we draw parallel to et plus delta t, then completing the vector triangle, we get delta et vector like this. This all is going to be useful in our derivation. Now have a look. We already derived this. V is equal to ds by dt into et. Let's differentiate it to get acceleration. So it becomes differentiation of the first term, d square s by dt square et plus ds by dt into det by dt. Now we will spend some time deriving or looking at what is det by dt. Now det by dt we want to work out, but before that just have a look at this. I think we'll agree that the arc delta s is rho delta theta, and therefore delta theta is delta s by rho. Now delta et by delta t in the by definition of derivative is limit delta t tending to 0 delta et by delta t. And this delta et being vector, it can be again written as delta et is magnitude multiplied by unit vector along delta et. Now, you see magnitude of delta et from this triangle can be seen as magnitude of et into delta theta. But we all know that et is unit vector, so this magnitude is 1. So magnitude of delta et is really delta theta, which we have derived here as delta s by rho. Now see what happens in the limit. Unit vector delta et, which is at the moment like this, it's not difficult to imagine that when this one comes close here, this delta et direction coincides with direction of normal to normal at this point, that is direction of en. Then limit delta t tending to 0, delta s by delta t become ds by dt, and therefore we can write delta et by dt as 1 by rho ds by dt into en. And this expression 2, if we substitute here, we get our required expression for acceleration. Acceleration d square s by dt square et plus ds by dt whole square upon rho into en. Now, for the remaining problem solutions which are there in the other videos, we are going to use these three equations. V is equal to ds by dt et, a is equal to d square s by dt square et plus ds by dt whole square upon rho en, and 1 by rho, that is radius of curvature of any curve, is given by this d square y by dx square upon 1 plus dy by dx whole square power 3 by 2. Now this we are not deriving it, it's a standard mathematical result and we are going to accept it. Now these three are going to be our basic equations for solving all the problems of kinematics of particles in curvilinear motion. So we are going to look at the problems in the next video. Thank you.